Alright, so there's two different things we need to kind of separate before we really get into the nuclear unit. The first one is a chemical reaction. For the term, you learned about them freshman year, you probably learned about them in middle school. We are going to get to chemical reactions later, but just not right now. So a chemical reaction is when elements kind of rearrange themselves. So in a chemical reaction, atoms are rearranged. So for example, if two hydrogen molecules and two oxygen molecules meet up, they can react to form two water molecules. So what's important here is that we still have in our products hydrogen. Okay, this is a gas, but this is water. That's a liquid. We're very familiar with that. In the case of hydrogen, though, it stays hydrogen. It's just rearranged in the sense that it's no longer hydrogen bonded to hydrogen alone. It's now hydrogen bonded to oxygen. So it is chemically changed and it underwent a chemical reaction. In the case of a nuclear change, though, the nucleons are what are changed. So our number of protons or our number of neutrons are going to change. They're going to turn into something else. And when that happens, what happens if the number of protons change for an element? The element changes. So we produce brand new elements. So for example, uranium-238, if it undergoes what we call an alpha decay, so if it releases an alpha particle, it's going to turn into a brand new element. It's going to turn into thorium. So this is different than a chemical reaction. In a chemical reaction like this one, hydrogen's in the beginning, hydrogen's there at the end. Oxygen is in the beginning, oxygen's there at the end. So we do not change the element identities. With nuclear reactions, with nuclear changes, we change the identity of the elements. So we talked about how elements can be unstable because the nuclear force isn't strong enough to hold that repulsion force together. If that happens, they lose either protons or neutrons or some other things could happen. And when that happens, it actually changes the identity of the element with the goal of reaching a more stable element. So there's 4 different types of nuclear change. We're going to go through and talk about them one at a time. There's natural decay, or what we commonly know as radiation. So when you hear the term radiation, hey, this thing's radioactive, this thing gives off radiation, what they're referring to is natural decay. There's also fission and fusion. Fission, this would be what they would use in power plants. It's also what they use in the atomic bomb. Fusion, you'll hear them talking about fusion sometimes. Cold fusion is a really popular power source that people are aiming for. The hydrogen bomb that they tested was also a fusion bomb. And then transmutation. All of those elements that you see on the periodic table that were man-made were developed by transmutation. And what we're going to talk about in this video then is the natural decay or radiation. So as the name implies, natural decays happen naturally. If you have an element that is unstable, which means it has too many protons, too many neutrons, or something else going on, it will naturally decay in order to reach a more stable element. And there's different types of radiation that can be given off for different types of decays. We'll talk about each one. In this first video, we're going to talk about the alpha decay and the beta decay. So the first one, alpha decay, we symbolize with this little fish right there. When an element undergoes alpha decay, its nucleus emits an alpha particle. And so it's something that comes out of the nucleus because of a repulsion force, fires off this alpha particle. So there's different ways we can symbolize an alpha particle, and it'll be a good way to kind of talk about what an alpha particle is. So the first way is just the little fish. Another way we can write it, so it means the same thing if we call it 2 protons and 2 neutrons. So that's really all an alpha particle is 2 protons, 2 neutrons together, and they're coming out of the nucleus. So if a nucleus gets too crowded, it'll fire off 2 protons and 2 neutrons together. Another way we can symbolize this then, 2 protons, that means it's helium, because helium has 2 protons, so we can also symbolize it as 4,2He. The 4 on top meaning it has a mass of 4, or it has 4 nucleons, 1, 2, 3, 4. The 2 at the bottom means it has 2 protons in it. And then the final way that we can symbolize it is 4, 2, and then the alpha sign. So it's kind of a conjoining of these two right here. It shows 4 nucleons, 2 protons, and then just the alpha symbol. So all 4 of those mean the exact same thing. The most common versions you're going to see are that one, and that one. This guy right here is just to kind of give you an idea of what they look like. So as an example, let's talk about neptunium. So neptunium, which has an atomic number of 93, so it has 93 protons and 238 nucleons. So Neptunium, it's really full inside the nucleus. It's going to want to get rid of something. And so it's going to want to then generate an alpha particle inside of its nucleus. And it will fire that alpha particle away. And so it's going to get rid of then through 2 protons and 2 neutrons from its nucleus. The way we would write this then is that Neptunium generates an alpha particle. So let's symbolize it with the fish for 2. And it's going to turn into something that has 2 less protons and 2 less neutrons. So hey, this is going to wind up being some of the easiest math you'll do in this class. If Neptunium, which has 93 protons, loses 2 protons, how many protons will the new element have? Well, 93 minus 2 would be 91. And then if something that has 238 nucleons, like Neptunium, loses 4 of them with its alpha particle, how many nucleons will it have left? It's going to have 234. So then what element is that going to be? How do we identify an element based upon its nucleons? Do we look at the total number of nucleons? No. Do we look at the number of protons? Yes, we do. So what element has 91 protons? If you look on your periodic table, it would be protactinium, or symbol Pa. So what this means then is that when Neptunium loses an alpha particle, so when it takes its 2 protons and 2 neutrons from its nucleus and fires them away, it's going to be left with 234 nucleons and 91 protons. The element would then be protactinium. Now keep in mind, protactinium itself may not be stable, probably more stable than Neptunium, but then protactinium itself can undergo a natural decay. Might be alpha decay, might be one of the different types. Let's try another example. So for this one, we're going to do thorium-232, which has 90 protons, 232 nucleons. Go ahead and pause the video and see if you can write this one out yourself. So show it giving off an alpha particle, and what new element will it turn into? Alright, so if it gives off an alpha particle, and I just wrote it differently, but remember, all of those mean the same thing. It's going to lose 4 nucleons, which means 228 nucleons, and it's going to lose 2 protons, which means 88 protons, and the element would then be radium. So a good way to safe check yourself is just follow this and treat that guy in the middle like an equal sign. Don't actually write it as an equal sign, never write it as an equal sign, but hey, 228 plus 4 equals 232. Is that true? Yes. Verified. 88 plus 2 equals 90. Also true. Come up here to this one, 234 plus 4 equals 238. 91 plus 2 equals 93. Alright, the second type of natural decay that we're going to talk about is a beta decay. So with a beta decay, and it's symboled like this sad emo 3, is when a nucleus emits a beta particle. And a beta particle, really guys, is nothing but a high-speed electron. But wait, Mr. Jones, you said that electrons are not found in the nucleus and they are not nucleons. How could they be involved in this? Well, it's a little bit trickier than that. So, ladies and gentlemen, I present to you a neutron. A neutron is neutrally charged, which means it has no charge. Well, let's think about a neutron then, instead of just being a neutral thing, as really something that has both positive and negative. And if you have both positive and negative, you're going to be neutral, just like a neutron. So if a neutron has positives and negatives, it can lose those positives and those negatives. So if a neutron fires off a negatively charged particle, aka an electron, pew, also known as a beta particle, what's going to be left? If it gives off its negative charge, all that's going to be left then is going to be a positive charge. So what happens with beta decay is a neutron shoots off a high-speed electron and turns into a proton. So an atom will actually gain 1 more proton, lose 1 neutron, and fire off an electron. So let's look at some ways that we can write a beta particle. So first off is just with that emo3. Another way that we can write it is just as a electron, because that's all it is. We can also symbolize it as 0 minus 1 e. And what that means in this case is how many nucleons does an electron have? Yeah, it has 0. There is no nucleus on an electron. And then the charge would be -1, so it would have a -1 number of positive charges, or a -1 number of protons. And that kind of tells us that it's a negatively charged particle with 0 mass. And then the last way we can write it is, just like we did with the alpha particle, we can write its number of nucleons in charge, and then the B. So all 4 of those would mean the exact same thing. However, the most common ones you're going to see are going to be the first one, the third one, and the fourth one. Okay, let's take a look at how this might look. So iodine 131 undergoes alpha decay, or beta decay. When this happens, it's going to be giving off a beta particle, so it's going to be giving off a negative charge, because one of its neutrons is going to turn into a proton and an electron. So that means it's going to be giving off a 0, -1 beta particle. And along with that, just like in the last case, it's going to generate a whole new element. So here we've got 131 nucleons and 51 protons. And let's remember that in beta decay, a neutron turns into an electron that's fired off, and then a proton that stays inside of the nucleus. So the proton does not go away, it stays in the nucleus where it belongs. The electron, though, doesn't belong in the nucleus, and so it's fired off in the form of a beta particle. So if this happens with iodine, how many protons will the new iodine have? Well, it started with 51, it gains 1 more from the beta decay, and so it will have 52 protons now. That's right, it actually increases in atomic number even though it gives something off. And it's because it gains another proton. Now, how will the number of nucleons change overall? We started with 131 nucleons. One of our neutrons turned into our protons. So overall, the number of nucleons does not change. It's a net loss of 0 because one of the nucleons turns into another nucleon. So as a result, the mass, the number of the nucleons, stays the same when a beta particle comes off. So what element then would have 52? Yeah, it would be tellurium, so Te. So when iodine undergoes a beta decay, it turns into tellurium 131. Now once again, to check this, guys, treat this middle guy as an equals sign. So 131 plus 0 equals 131. 52 plus -1 equals 51. So there you go. We checked our answer. You can also do this the other way if you wanted to figure out what that number was. 51 equals -1 plus what number? 52. So beta decay inherently ends up being one of the trickier ones for students. So here's 2 more practice problems. Pause the video, give these both a shot. They both undergo beta decay. Resume the video to check your work. So if krypton undergoes beta decay, it's going to lose or gain 1 proton because one of its neutrons will turn into another one, and its mass will stay the same, so it would turn into rubidium-81. And when magnesium undergoes beta decay, it's going to turn into aluminum-23. And the last part of decay that we're going to talk about is a gamma ray emission. And this is different than the other ones because it doesn't actually change the atom at all. Rather, it's just a form of energy that's given off while an atom's undergoing decay. So a gamma emission is really just a high-energy photon that's emitted during decay. So while an element's undergoing alpha or beta decay, it'll shoot off that alpha particle, shoot off that beta particle, and it'll also release this high-energy photon. And so this would be a wave of energy, just like when we talked about other waves of energy. So it's going to have a wavelength, it's going to have a frequency, and it's going to have a certain joule worth of energy. It is symbolized with a fancy-looking Y. And it can also be written as 0, 0, fancy Y. And 0, 0 because it has no mass and it has no charge. It's just energy. Literally just a wave that comes off. As a result, it's actually one of the most dangerous forms of radiation because it's just straight up energy. If there was laser guns that we could use, it would be in the form of gamma emissions.